The last recording for the cardiovascular chapter, we're going to talk about blood. So we've talked about the pump, which is the heart. We've talked about the channels that carry the fluid, which is your blood vessels. And now we're going to talk about the fluid in the pumping system, which is your blood. And specifically related to exercise, we've talked about blood as a means for transportation. Okay? It transports gases, oxygen, CO2, nutrients like glucose and free fatty acids, hormones, etc. So blood has a huge role in transporting things around your body. We've also talked about blood in its role for temperature regulation, because as heat is produced in your body, that heat is absorbed by the blood, carried to the surface of your skin, where that heat can be dissipated and removed from the body. We've also talked about blood's role in acid-base balance. Remember that in your bloodstream, as hydrogen ions accumulate, they bind with bicarbonate ion, which comes from the kidney. Gets rid of the hydrogen ions, but in the process produces CO2 and water, and then we can exhale. We can get rid of that CO2. So blood has an important role in acid-base balance or pH balance, because if hydrogen ions get too high, pH gets too low. As far as blood volume, the total blood volume in your body varies with size. The average man has a blood volume of 5 to 6 liters. The average woman has a blood volume of 4 to 5 liters. So on average, people have about 5 liters of blood in their body. Blood volume increases with lean body mass. So people with more lean body mass have greater blood volume. And it also increases with endurance training. We'll say more about that. If you put your blood into a centrifuge and we spin it, it separates into two major components, which are your plasma and your formed elements. Your plasma is mostly water, okay, and your formed elements are mostly made up of red blood cells. So this is a centrifuge, and after you get your blood drawn, that's where your test tubes go. They spin it really fast, and the heavier portion of your blood goes to the bottom, and we call those the formed elements. And I told you that your formed elements are primarily made up of red blood cells. And then the less dense portion of your blood is your plasma, and that's mostly water. It's about 90% water. One of the measurements that is commonly taken with blood is something called hematocrit. And hematocrit simply measures what percentage of your total blood volume is made up of the formed elements, which again is primarily red blood cells. So it's a very simple calculation. You take the amount of formed elements and you divide it by the total blood volume, and that's going to tell you what percentage of your total blood volume is made up of formed elements. So another example, if we had a test tube and we had 50 milliliters of formed elements, and if we had 60 milliliters of plasma, we would have a total of 110 milliliters of total blood volume. So to calculate hematocrit, you would take those formed elements, you divide it by the total blood volume, and in this situation, we would get a hematocrit of 45.5%. And hematocrit gives us a good indication of the thickness of your blood, because if the formed elements are a greater percentage of your total blood volume, your blood is going to be thicker and more viscous. So the higher the formed elements, the higher the hematocrit. At the same time, you might be able to see that if we increased plasma but didn't increase the formed elements, we would get no change in formed elements, but we would get an increase in total blood volume, and therefore we would see a decrease in hematocrit. So when red blood cells rise, we get an increase in hematocrit, and when plasma rises, we get a decrease in hematocrit, assuming nothing else changes. Just some interesting facts, not numbers you need to know, but just to give you an appreciation. The average human has 4 to 6 billion red blood cells in their body, and each of those red blood cells contains about 250 million hemoglobin. Each hemoglobin carries 4 iron. Each iron contains 1 oxygen, and therefore each red blood cell binds about 1 billion oxygen. Okay. You multiply that by the number of red blood cells we have in your body, and you can see that we have billions and billions of oxygen molecules in our body. So when we talk about blood, let's focus in on blood viscosity. That's why we talked about hematocrit. So a higher hematocrit means more viscosity. Okay, it means that a greater portion of your total blood volume is made up of the formed heavy elements, or your red blood cells, which is going to make your blood more thick. And if you remember back to the discussion of peripheral resistance, we talked about viscosity. So the viscosity of your blood is going to affect peripheral resistance. And we've also talked about peripheral resistance because it affects blood pressure and it affects the rate of flow in the body. So the viscosity of your blood is an important factor to consider for both health and performance. So if we increased viscosity, okay, we would increase peripheral resistance. Okay, and by increasing peripheral resistance, you increase blood pressure. Okay. At the same time, if you increase peripheral resistance, you decrease the rate of blood flow. Okay, so keep those in mind, and that's really the importance of these formulas, and knowing these formulas is not to use them with numbers to make any calculations, but to understand the effects of the change in one factor, like viscosity, on other factors, like blood pressure, which can affect your health, and the rate that your blood flows, which can affect your performance. So let's talk about 3 different factors that increase viscosity. In other words, they make your blood thicker and heavier, increasing the hematocrit. And one of them is dehydration. Okay, dehydration is a loss of water. And remember that your plasma is made up of mostly water. So if you're dehydrated, some of that water is going to come from your plasma. And if you lose plasma, you lose total blood volume. Okay, so remember that we've got the formed elements over total blood volume equals hematocrit. Okay, so if you are dehydrated, you're going to lose some of your total blood volume. Okay, your formed elements are going to stay the same, and therefore your hematocrit is going to go up. Your blood is going to become more thick. Okay, and if hematocrit goes up, viscosity goes up. Viscosity goes up, peripheral resistance goes up, which is going to slow the flow rate. Okay, so dehydration can be detrimental to performance, because if you're dehydrated, your blood is going to flow slower, and therefore you are going to deliver oxygen, glucose, fat slower. You're going to remove CO2 and hydrogen ions slower. And those things, as you know, can affect performance. As far as how much dehydration can affect plasma, you can get up to about a 10% decrease in plasma, and in extreme conditions even more, just based on dehydration. Another factor that involves viscosity, and this is not related to exercise, but it's interesting to think about. When somebody has lung disease, they have trouble getting air in and out of their lungs. So what happens with lung disease is that people end up having low oxygen levels in their blood. Okay, and this triggers a negative feedback response. If the blood contains less oxygen, your body is going to try to find multiple ways to increase the oxygen level. And remember that red blood cells carry oxygen. So one of the things the body's going to try is to increase the reproduction of red blood cells, because maybe oxygen is low because you have the inability to carry it. So people with lung disease have an increased production of red blood cells. Okay, when red blood cells increase, okay, your formed elements increase, and this ends up causing an increase in hematocrit, okay, which causes an increase in peripheral resistance, okay, increase in viscosity, increase in peripheral resistance, increase in blood pressure. So we often see that people with lung disease develop hypertension. Another factor that affects blood viscosity is something called blood doping. Okay, and there's different ways to do this. The original style of blood doping was that an individual would draw some of their blood, maybe 500 liters of milliliters, not 500 liters, 500 milliliters of blood, and let their body regenerate their own blood. So it takes time after you, like when you donate blood, you donate about 500 mils. Within about 24 to 48 hours, your plasma is back to normal, but it takes about 6 weeks for your red blood cells to come back to normal. So 6 weeks or so before a competition, they draw their blood, they allow their body to regenerate red blood cells, and then they take their blood out of the freezer, and they usually keep only the red blood cells, and they infuse those red blood cells back into the body. So now all of a sudden you have many more red blood cells than you had before. And this is useful to performance because it increases your oxygen carrying capacity. Okay, if you can carry more oxygen, you can deliver more oxygen, and maybe you can use more oxygen, and therefore you can use aerobic or oxidative energy production at higher intensities. And remember, that's a fatigue-resistant system, so that's going to increase your endurance performance. And it's pretty powerful. It works really well, but it is technically illegal because it's dangerous. Because keep in mind that if your red blood cells are rising and your hematocrit is rising, okay, this is causing your peripheral resistance to rise, which is going to reduce your flow rate. Okay, that's one problem. The second problem is an increase in viscosity, increase in peripheral resistance is going to increase blood pressure. That's another problem. So you get these athletes who have, if they overdo it, and there's kind of a fine line there in terms of overdoing it, but the cutoff tends to be about a hematocrit of 60. The blood gets so thick it could literally stop flowing, and the blood pressure is really high and could lead to a heart attack. And there are many documented instances of people overdoing blood doping and ending up with a heart attack because they overdid it. So it's pretty scary, and that's the primary reason why it's illegal. Plus, it's not natural. The way that people blood dope now is they use EPO, which is a hormone that produces red blood cells. It stimulates the production of red blood cells. It's given to cancer patients who are going through chemotherapy because chemotherapy kills off red blood cells. So the cancer patients take EPO to keep their red blood cell production up. But athletes can get a hold of this and take it, and it's much easier than the old blood doping where you had to draw your blood, wait 6 weeks, and infuse it back in. So they can get a hold of EPO illegally and increase the red blood cell production. So again, it's illegal and it's also dangerous, but you should be aware of it. Okay, so those are factors that increase viscosity. And again, the potential problems with an increase in viscosity is increase in peripheral resistance, which causes a decrease in flow rate, which could be dangerous to your health and can also negatively affect your performance, and increase in your blood pressure, which if it goes up too high is a health danger. It's okay if your blood pressure goes up during exercise, but if your blood is viscous all the time, your blood pressure is going to be high all the time. And this is very stressful on the body to have high blood pressure 24 hours a day, day after day. So let's talk about the factors that decrease viscosity. All right, got a clean page here. So one of them would be anemia, which is pretty obvious. So what anemia is, different causes of anemia, but one of the most common causes of anemia is low red blood cells. Okay, for some reason the body's not producing enough. And like I said on the last slide, this happens often with people going through chemotherapy, where their body, a lot of the red blood cells are killed off in chemotherapy. Their red blood cell counts are low. This is going to decrease viscosity, okay, because if you remember again, we've got the formed elements, we've got the plasma. Hematocrit, or thickness, is the formed over the total blood volume. Okay, and if your formed elements decrease, hematocrit is going to decrease. Okay, and if hematocrit decreases, that means your blood is less viscous. Okay, the problem with anemia is that you have low blood cells. Okay, so you might be thinking, oh, low hematocrit, oh, low peripheral resistance, high blood flow. Okay, that's great for performance, except that if you have low red blood cells, you're not going to be able to carry as much oxygen. So anemia is not good for performance. The other thing that we see in terms of decreasing viscosity, and this is a good thing, is that we see that people who are endurance trained have an increase in red blood cells, but an even greater increase in plasma. Okay, so we do see a small increase in red blood cells with training, but we see a large increase in plasma with training. Okay, so if red blood cells increase, but total blood volume increases even more because of the plasma, what we're going to see is a decrease in hematocrit. Okay, so increase in plasma, increase in red blood cells, but the increase in plasma is greater than the increase in red blood cells. So the overall effect of endurance training would be a reduction in hematocrit. Okay. Reduction in hematocrit means a reduction in peripheral resistance, which means an increase in blood flow rate. And that is going to speed the delivery of oxygen and other nutrients, and the removal of CO2 and other things that need to be removed to prevent fatigue. That is blood.